All right, everybody, we'll go ahead and get going. Last hour was an unmitigated disaster. Hannah, you were here, so you know that it was a disaster. I started out trying to show something in YouTube that I did last year and when I was teaching 352 in the winter. And
there were a lot of adaptations on the fly.
Yeah, and then after a lot of technical difficulties, we finally got going, and then with 5 minutes left, my computer died because guess who forgot to plug it in at the beginning of the lecture? So things are definitely not going as planned. Hopefully this will be a little smoother than last time. I'm going to unfortunately attempt fewer bells and whistles, so I'm sorry if it's boring, but I'm going to play it safe. That being said, I used to, when in the depths of the pandemic, which we're still in, but at the beginning of 2020 when BYU went remote and I was suddenly lecturing from home, I put a few little sort of what I thought were entertaining bits at the beginning of each video, and I was attempting to show one of me doing the scene where Gollum is talking to Smeagol in one of the Lord of the Rings movies, and it was I think my dramatic high point of my entire life, but I couldn't get it to work here. So I will send out links to everybody so you can see that. It's not that great. Feel free to leave suggestions for feedback in the comments so that I can improve my performance. Go ahead.
Did you send out a link for your Star Wars scene?
The Star Wars one as well?
It's really
Have you seen it? Okay, yeah. So the Star Wars one, me and David Michaelis do on Halloween. He dresses up as Kylo Ren or a Jedi, and I bust out my Darth Vader costume. That's a whole other story with my red lightsaber. And we've done it for 2 or 3 years now, and the production value keeps increasing. So this year, in addition to having explosions, we added music and pre-recorded dialogue, because it turns out that it's kind of tough when you're a professor and you're inside a Darth Vader mask and you're trying to swing a lightsaber at someone to remember your lines and then to say them loud enough for everybody to hear. And Michaelis and I often miss each other when we're swinging our lightsabers, because also with masks, when you're trying to remember your lines, it's hard to know where you're swinging. So anyway, this year the production value is quite a bit higher, though I still almost caught on fire and definitely tripped over my own cape. So that was kind of fun. So yeah, it's on the YouTube channel. You can watch. And maybe come up with suggestions for next year's show. If you've got a good enough suggestion, I could probably convince Michaelis to give it a try here, but we'll see. I'm always looking for an excuse to put on my Darth Vader costume. Okay, so our theme over the past few days has been that shapes of organic molecules are what give them their function and properties. And so we've been talking about conformations as a way to think about molecular shape. But there's another element too, that another aspect of molecular shape that we haven't talked about, and that's our theme for chapter 5. And we can actually introduce it the way with a couple molecules we were talking about last time. Cellulose and starch. And if you compare these two molecules atom by atom, they have the same connectivity. That means that if you go to atom 1 and you ask, what is atom 1 in cellulose attached to? And you would say an oxygen, another oxygen in the ring, a carbon in the ring, and a hydrogen. And if you went over here for starch, you'd come to the same conclusion. And you can do that all the way around, same connectivity. Nevertheless, you can see they have different shape. And that's easier to appreciate in this side view. But you can also see it if you draw, say, one of these subunits from cellulose. I won't draw the whole molecule. I'll just draw one subunit. So this is one of them from cellulose, and then we draw the second from starch. Oops. And you can see that the difference between the two has to do with the whether or not the oxygen at carbon 1 is up or down. Sorry. Okay. They differ at that particular carbon. Same connectivity, but different shape. And by different shape, we mean more or less permanently. In general, we're not going to say that, well, what if I drew this OH group on this side instead of on that side? Does that mean they're different shape? No, because you can have free rotation around sigma bonds, carbon-carbon sigma bonds in organic molecules. So different sort of permanent shape, but same connectivity. We've got a word for that. They are not only isomers, they are stereoisomers. Stereo because of the three-dimensional shape, isomers because they've got the same connectivity, same molecular weight, same number of atoms. All right. Is carbon 2 supposed to be up or down? I'm sorry about that. Carbon 2 on the right was supposed to be down. That's my mistake in going from one to the other. Okay. So there are going to be, in our experience, two different kinds of stereoisomers. And the kind that we have here in cellulose and starch, they are called diastereomers of each other. The term diastereomer and stereoisomer refers to a relationship between two or more molecules. It makes no sense whatsoever to ask, is this molecule a diastereomer? Because the chemist will be waiting for you to say, of what? Is it a diastereomer of this other molecule? So it describes the relationship. It'd be like, it's the same thing as asking, is this methyl group cis? Well, to what? Is it cis to this methyl group or trans to that methyl group? Who knows? So it describes a relationship between two groups. There will be another class of stereoisomers, and it will be called enantiomers, and we'll explain what that is. Diastereomers are stereoisomers that are not mirror images of each other. And they have, by definition, different chemical and physical properties. They can react differently. They can have different melting and boiling points. They're different because of their shape. Some examples of diastereomers that you have already seen include E and Z alkene stereoisomers. So cis or this Z alkene is a diastereomer of this E alkene. Another example is cis and trans generally. For example, having two methyl groups on the same side of the molecule versus opposite sides. These two are diastereomers of each other. And there are other potential examples too. We'll deal with them a little bit later. All right. In contrast, enantiomers are stereoisomers that are mirror images of each other, but are nevertheless not the same because they have different shape. And this can be difficult to see. The classic example of mirror images that are nonetheless the same thing is your hands. Your right hand is the mirror image of your left hand. more or less. I mean, there are differences, but you can line up the thumbs and the fingers and the palms, but you can't line up the back of the palm. Or alternatively, you can line up the back and the back of the hand and the front of the palm, but not the fingers. Okay? And you can try until you're blue in the face and until you're dead and gone. Through all eternity, you can try to do this, and you will never superimpose your right hand versus your left hand. It's just an eternal principle. Okay? It's the universe that we live in. But how does this apply to molecules? And the easiest way to do this, the classic way to evaluate whether two molecules are mirror images of each other, is simply to draw one and then draw the mirror image. Now, you can do this with a model set if you have one, but it's also useful to be able to do it on paper. So here is a carbon molecule, and for convenience, we're choosing just 4 different things attached to this carbon. It may be helpful to sort of color in the various groups just so that we can see that they're different from each other. And then we'll pretend that this molecule is standing in front of the mirror. Now let's draw the mirror image. So the hydrogen and carbon, the bond here between carbon and hydrogen is in the plane of the page. Chloro would need to be pointing to our right because that is a reflection of the image on the left. And then we would have fluoro coming out this way and bromo coming out that way. Now, this is a pretty important skill, and it may be difficult at the beginning, but it's important to practice. Can you see how these two things are mirror images of each other? Everything on the left is a reflection of what's on the right and vice versa. Now, how do you tell whether or not they're different? Well, again, you can make a model and play with it, or you can develop some paper tools for comparing. So let's imagine getting our molecular tweezers out and holding on to that hydrogen with the dangly claw of doom, and then let's spin around by 180 degrees. Okay? And then let's redraw what we would have. Now that process of spinning would move chloro here. So far so good. It looks like we're closer to lining up hydrogen and chloro. But let's think about what the other groups are going to be on the carbon. Fluoro used to be pointing out in front. If we spin that carbon around 180 degrees, where is the fluoro going to be? Pointing in the back. So now fluoro occupies the dash, and then bromo occupies the wedge. So now we've spun that around, we can try to overlay it with its mirror image, and we can overlay the hydrogen and the chlorine, but we can never overlay all 4 groups. Similarly, we could flip it in another way and line up the bromine and the fluorine, but then the hydrogen and the chlorine would be in the wrong place. Okay? So these two are mirror images of each other. Nevertheless, they are not the same, and therefore they are enantiomers of each other. So the definition of enantiomers is 2 molecules that are mirror images but are nonetheless not the same. Yeah?
For enantiomers, are you assuming that the bonds that won't rotate or that they don't rotate permanently?
So for enantiomers, are we assuming that the bonds don't rotate? No, rotation's allowed, but you can't interchange one enantiomer with another without breaking bonds. In other words, there's no way to get the molecule on the right to be equal to the molecule on the left without popping the fluorine off in the back and putting it back on in the front. It means you would need a chemical reaction to convert one enantiomer into another, not just bumping around or rotating in solution. Okay? Enantiomers are mirror images of each other, and so they will have the same chemical and physical properties, though they will not have the same biological properties for reasons we will talk about later. All right, so we're going to introduce a new term to describe molecules that are not the same as their own mirror images, or rather molecules that have an enantiomer. We're going to introduce this adjective, which is chiral. A molecule is chiral if and only if it is not the same as its mirror image. A chiral molecule will, by definition, then have an enantiomer. All right? And if two molecules are enantiomers of each other, they are both chiral. All right. Questions about those definitions? You will sometimes hear older organic chemists and then in many cases, biologists refer to chiral molecules as having a chiral center. We no longer use that term in organic chemistry because chirality, being chiral, describes a geometric situation. And if one part of the molecule is chiral, the whole part of the molecule is chiral. So it doesn't make sense to say, well, this carbon is a chiral center, whereas this chlorine is not. No, the whole molecule is chiral. All right? As we talk about chiral molecules, it will become useful, though, to define something called a stereogenic center. That is, part of the molecule that generates options for shape or stereochemistry. And we're going to define a stereogenic center, or actually we're just going to call it a stereocenter for short, as an sp3 atom with 4 different things attached. Why do we care? Well, that is a classic situation in which you could make a molecule chiral, is if the molecule has a carbon with 4 different things attached. Notice that's what makes this molecule chiral, right? A carbon with 4 different things attached. In contrast, a molecule, say, that's trigonal planar with 3 different things attached cannot be chiral because it is its own mirror image, right? Molecules that have sp2 hybridized carbons are trigonal planar. The plane of symmetry is the page here. It is the same as its own mirror image. So, identifying stereocenters, or sp3 hybridized atoms with 4 different things attached, will help us in talking about chiral molecules. And there's a couple of rules of thumb that will always be true. The first is a molecule with only one stereocenter must be chiral. A molecule with 2 or more stereocenters might be chiral. but might not. And it just depends. That is not comforting to those of you that want to get these kinds of questions right on exams. So I want to show you, rather than just tell you about these things, by doing a few practice problems. So, is a molecule chiral? Is one of the questions that is sort of fun to ask. Is a molecule chiral? And the fail-safe method that will always work when asking is a molecule chiral is to draw its mirror image and then see if they are the same. Okay? There will be some shortcuts, but this one will always work. So as an example, we demonstrated above by drawing the mirror image that molecule A is chiral, as is molecule B, and that they are enantiomers of each other. Now, what about this molecule? Is that molecule chiral? Well, fail-safe method is let's draw a mirror plane, and then we'll draw on the right everything we drew on the left in the same orientation. Oh, that was boring. You see that those two are reflections of each other. Nevertheless, they are exactly the same. So we would say that molecule 1 and molecule 2 are not enantiomers. They are the same. And therefore, that molecule 1, is not chiral. Now, you'll hear people use a term for not chiral, that is achiral. And you can use that term. This molecule is achiral, though I've found in class I confuse myself when I do that because I think I'm talking about a chiral molecule instead of a molecule that is not chiral. So I'm just going to use not chiral to avoid confusing myself. You are welcome to use achiral. Watch out on multiple choice exams too. It's tempting when option A is chiral and option B is achiral to get totally mixed up. So just pay attention. Now, another way we could have identified that this molecule was not chiral. Yeah, so Jacob, you're saying to be chiral, a molecule has to have a mirror image that is not the same as itself? Yes, that is the definition. Now, a shortcut for identifying molecules that are not chiral versus molecules that are chiral is to look for stereocenters. That is, if we had that molecule above and didn't want to go to the trouble of drawing its mirror image, if we concluded that carbon that is circled there is a stereocenter and the molecule only has one stereocenter, then it must be chiral. End of story. Okay, so if a molecule has one and only one stereocenter, it must be chiral. You can actually skip to that without even drawing the mirror image. Let's try to apply this shortcut to our molecule 1, which we identified before as being not chiral. So let's ask, is carbon atom A here, is that a stereocenter? To do this, you've got to determine whether it's attached to 4 different things. So sometimes color can be useful for this. Hydrogen is different from a methyl group. And methyl groups are different from CH2 groups. Are these two carbons the same? Well, we're not sure until we investigate the whole chain. If there were something else here that was not a hydrogen, then no, carbons B and C would not be the same. But in this case, they are the same. We can A, B, C, D. I realized I changed how I was numbering them. How do you know that B and F are the same? They just are. We've been here before. Yeah, go ahead.
Because they're part of a ring and they're all connected to the same carbons that end up counting the same either way.
Okay, so that the answer here in class was that B and F are the same because they're connected to the same things. And then if you go out another atom, those atoms are connected to the same things. And you go out another atom, oh, you've got the same atom. In order for two groups to be the same thing, they got to be the same all the way out. All right, so if you wanted to, if this was difficult to see, you could go here and say, okay, B is attached to 2 carbons and 2 hydrogens. So is that. In fact, you could use your E and Z approach about are these two things the same to determine this. And we'll go back and actually do that when we start wanting to talk about how to describe one stereocenter versus another. Nevertheless, yes, B equals F and E equals C, and of course D is the same as itself. Therefore, carbon A is not a stereocenter. And similarly, you could go around and convince yourself that none of the other carbons there in that molecule were stereocenters. All right. Second shortcut. Well, actually, let me show you a case where looking for stereocenters may not help you. Carbon 1, 2, 3, 4, 5, and 6. So probably without a huge amount of trouble, we can say that 6 and 3 are not stereocenters because each of them are attached to 2 hydrogens, 2 of the same thing. Same with carbons 5 and 4. What about carbon 1? Is that a stereocenter? Is it attached to 4 different things? Again, it's easy to see that methyl and hydrogen are different. What about 6 and 2? Are those the same or are they different? Different, and use your EZ procedures, honestly, to figure this out. They're both carbon. So then look at what they're bonded to. 2 is bonded to 3 carbons and a hydrogen. 6 is bonded to 2 carbons and 2 hydrogens. So they are not the same. They are different. They have to be different. And therefore we would say carbon 1 is a stereocenter. How about carbon 2? Is that also a stereocenter? By the same reasoning, yes, carbon 2 is a stereocenter. All right, now, that gets us into a bit of trouble if we forget that if you have 2 or more stereocenters, it might be chiral, but you got to check. All right? So stereocenters as a search for chirality only works if there are 0 stereocenters or 1. If there's 2, you still got some work to do. So we'll fall back to the fail-safe, which is let's draw the mirror image. Here is our mirror. Color, 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 blah, 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 blah. And we'll draw the mirror image here. Okay, and now we can go back to our fail-safe. Let's move things around and see if they're mirror images of each other. There are a couple of ways that you can do this. Imagine putting an axis down the molecule, sort of skewering it down the middle of the ring and rotate 180 degrees. That would get you to here. And lo and behold, that's the same as this, right? Just by spinning that around. We call that the, I was going to say record spin, but you guys, maybe some of you are into vinyl, I don't know, but mostly records you don't know, and mostly CDs you don't know either. So it's a disc that spins around, okay? Please stop patronizing us, Dr. Price. Yeah, okay. So you can either do that, or if you want, you can do double pancake flip action. So take this molecule and take your molecular spatula and flip it over that way. And that would get you here. And it looks like it's different, only now we're going to flip it over this way. And it's the same thing. So it's good to have some molecule moving tools in your toolbox to help you determine whether two things are the same. Now, there is another shortcut. I'm sorry, did you have your hand up?
Yeah, if the two methyl groups were trans instead of cis, would it still be not chiral?
Yeah, if the two molecules were trans instead of cis, would it be not chiral? Well, we can do that. Okay. We would still conclude that yes, carbons 1 and 2 are stereocenters. But then we would draw our mirror plane and then we would need to, again, sort of manipulate things in our mind to convince ourselves that it's not the same. Do the 180-degree vinyl spin, and you end up with this. Okay, well, and then do pancake flip in this direction, and you end up with this. And then you think, okay, still doesn't look the same, fine, let's try it in this direction. Uh-oh. This is an interesting molecule. Doesn't matter how many times you pancake flip it in that direction, it's the same thing. So these two are not the same, but they are mirror images of each other. Mirror images, but not same. That is, they are both enantiomers of each other. And yes, this molecule is chiral, and so is this one. Yeah. So a shortcut that you can use, that you can use when a molecule has two or more stereocenters, instead of drawing the mirror image, I mean, you can still do that, and that's always a fail-safe. The shortcut number 2 is look for planes of symmetry in the molecule. So to illustrate that, we'll just actually do this with one of our drawings of the cis dimethyl molecule. Can you identify a line or a plane that would separate the molecule into two equal halves? Just horizontally, right? We would conclude that methyl group A is the same as methyl group B, that carbon 1 is equal to carbon 2, that carbon 3 is equal to carbon 6, and that carbon 4 equals carbon 5. And it turns out that looking for a plane of symmetry in this way is a quick way of seeing whether a molecule is the same as its mirror image. Try to illustrate that here, because if a molecule has a plane of symmetry, then you can actually pretend that that plane of symmetry is a mirror, move it here, and it is its own mirror image. Any molecule that has a plane of symmetry in it must be its own mirror image. Maybe that's a good rule of thumb. Any molecule with a plane of symmetry must be its own mirror image, and therefore is not chiral.
Is there any exceptions to that?
No. Are there any exceptions to that? No. Yes?
Does that plane of symmetry need to be between the two stereocenters?
Does the plane of symmetry need to be between the two stereocenters? In this case, yes.
In other cases, though?
Well, in a molecule with two or more stereocenters, in order for it to be not chiral, those stereocenters will have to be reflections of each other across a plane of symmetry. Yeah. Some comments from the chat about how useful model kits are. It is. You may wish to get a model set and play with it. The model set, in my mind, is a little bit like a seer stone or a Urim and Thummim. Joseph needed those in the beginning to get revelation and to do translation. After a while, he didn't need them anymore because he grew accustomed to the process of revelation. Similarly, at the beginning, models are very good for helping you visualize the three-dimensional shapes of molecules. You will eventually get the skills such that you can draw on paper and see in your mind's eye what the shape actually is. But until then, it's probably a good idea to have a model set to work with. I don't have a specific one that I endorse. Some of them are easier to use than others. Just don't spend a lot of money, and so on. I do have some models in my office, a model set of these molecules in my office, so you're welcome to come by and build things. It used to be a bigger model set, but my children would come to my office and build strange things and then ask if they could take them home, and I fell for it, and then I never saw them again. So anyway, and you're always welcome to use molecular models on exams, assignments, and so on. Okay. Actually, let's see, did we get, yeah, any other hands that I missed here or at home? So we've got actually now a chance to talk about enantiomers versus diastereomers. So let's redraw the two trans enantiomers. Note that we could draw the two trans enantiomers like this, or we could draw the other one like this. Those are both the same. In this molecule, we have each of these molecules has two stereocenters. I'm going to erase the other one because it isn't going to matter for our discussion. And each time you have a stereocenter, that individual stereocenter can be arranged in one of two possible ways. So every time you have a stereocenter, there's a chance for two different configurations. So if a molecule has two stereocenters, there might be a chance for four different configurations. Unless, as we've shown here, there's a hidden plane of symmetry that makes one of those molecules the same as its mirror image. As we've said, these molecules are enantiomers of each other. What is the relationship between A and B then? Good, it's got to be diastereomers. And that's a definition that I remember struggling with and don't remember exactly what it meant. All you need to know is are two molecules stereoisomers? That is, do they have the same connectivity, but they're not the same? The different shapes? That's the first question. Second question is, are they enantiomers? That is, are they mirror images of each other? And if the answer is no, then they must be diastereomers. You only have two kinds of stereoisomers, enantiomers and diastereomers. So I won't dare try this, but maybe I'll send out the link. My children grew up with VeggieTales. Does that sound familiar to anybody? Vaguely? Okay. So in VeggieTales, there's Bob the tomato and Larry the cucumber. And Larry the cucumber has sort of the intelligence and temperament of a 3-year-old. And Bob seems to be a little bit older and a little bit more exasperated. And sometimes Larry sings silly songs. Larry always had a buck tooth, and Bob always looked sort of stressed. Anyway, there was Larry Boy was the best. Yeah, they had a superhero envisioning of Larry the cucumber, in which he wore some kind of purple crested hat with plungers on the sides, and the plungers could shoot out, and he could fly like Spider-Man, or fling them like Spider-Man. That's neither here nor there. My son was Larry Boy once for Halloween. Amber made this elaborate felt headdress that he wore not only on Halloween, but every day thereafter until it fell apart. In any case, one of Larry's silly songs is about if it doesn't have a tail, it's not a monkey. And so you should look at this. If it doesn't have a tail, it's not a monkey, even if it has a monkey kind of shape. If it doesn't have a tail, it's not a monkey. If it doesn't have a tail, it's not a monkey, it's an ape. And that's how Larry's classifying animals, and they go through this argument about how a cow has a tail, then it's a monkey. A camera doesn't have a tail, then it's an ape. But that kind of binary view of stereoisomers is useful. So once you watch that, I'll send out the link, and once you watch it, you can sing to yourself, if it's not an enantiomer, it's a diastereomer, even if it's got an enantiomer kind of shape, and that can be your new mantra as you go to sleep at night, instead of draw the conjugate base. That one's getting boring by now, so now you can work on enantiomers versus diastereomers. So I want to show you some of my evil tricks by which I will try to deceive you on the exam. Evil trick number 1 is the concealed not chiral molecule. I sometimes call this the meso trick. So, as an example, let me give you this one. 1,2-butane diol, or no, 2,3, whatever, butane diol. Is that chiral? Well, let's have a look. We could see, are there stereocenters? And if we did that, then yes, we would see oxygen versus carbon, methyl group, versus hydrogen that's not shown, but now is, versus the other carbon. And in fact, we would conclude that both of those groups are stereocenters. 2 stereocenters tells us might be chiral, but might not, so we've learned nothing. Now let's draw the mirror image. Oops. Okay. Those are both stereocenters as well. Now I can try to rotate this around and see if it's the same thing. And it kind of looks like it's not. Now, one thing that would save me at this point is if, in addition to thinking about the spinning vinyl motion and pancake flipping motion, thinking about rotating around carbon-carbon bonds. If I look for a plane of symmetry in this molecule, it doesn't look like there's one. But that's because I've drawn this molecule in a conformation where the plane of symmetry is difficult to see. So let us rotate 180 degrees about this central carbon-carbon bond. That would bring the methyl group that was pointing out to our right, pointing straight up now. The OH group here is still down. The OH group that used to be up would now be down. Now do you see a plane of symmetry? Right there. And anytime you have a plane of symmetry, that means that the molecule is the same as its mirror image. So, what is the relationship between these two groups? Between these two molecules? Deception. There is no relationship. They are the same molecule. They are mirror images that are the same as each other. We have a word, by the way, for molecules that have stereocenters but are nonetheless achiral or not chiral. Have stereocenters but not chiral. We call those mesocompounds, and I'm not sure why. But the concealed mesocompound is a classic way for me to, let's see, where's the chat function? Classic way, I want to make sure I'm getting questions, for me to deceive you. And for me to conceal compounds that are not chiral and make them look chiral. Okay? I think that's about it. Any last questions? Now that I've said that's about it, nobody wants to speak up because we don't want to delay ourselves. So with that, I guess we'll call it good, and I will see you on Tuesday, which is Pretend Monday, because Monday is President's Day, I guess.